So here's an interesting consequence of the way refraction works. When you look at something like a pencil in water, it looks like the pencil is bent. When you look at something in a swimming pool, like a coin or a ball or something at the bottom of the pool, it actually looks closer than it really is. This is called apparent depth. Consider the pencil in water. The light rays travelling from the tip of the pencil are bent when they get to the surface on the way to your eye. Because the air is thinner, optically speaking, the light rays are bent away from the normal. Of course, your eye doesn't see the bend in the light rays. Your eye assumes that those light rays came from this point here, the point where those diverging light rays meet, exactly the same as a virtual image from in a lens or a mirror. So your eye sees the tip of the pencil down here, it actually sees it as being up there, and so on all the way along this pencil under the water. As a result, when you look at the pencil, it looks like the pencil's bent. In fact, the light rays are bent. It turns out we can actually describe the change in this depth, the apparent depth of the tip of the pencil, or the apparent depth of a ball or something at the bottom of a pool, using some maths. This is the apparent depth formula. Actually, that's a simplification. This n is really the relative refractive index going from material 1 to material 2. It's just that most of the time we're the ones looking, and we're looking in air. So when we look in air, N1 is 1, so this is just N2, or the refractive index of water. So this formula tells you the relationship between the true depth, the real depth, and the apparent depth of the image. Now, I said it depends on both refractive indices. Of course, if we're in water and looking at something in the air above, yes, we'll get a change in apparent depth. Actually, it'll look further away in air, but we get an additional effect due to the total internal reflection. But that's a topic for another video.